which is the synthesis of azole violet. And azole violet is a dye. And human beings have been messing around with dyes for an extremely long period of time. Now, throughout most human history, dyes came from natural sources, primarily plants, some animals, and other things, but they were natural sources. And this meant that certain dyes were limited and many of them were expensive. And so when chemistry started to mature into a full-blooded science where rules and everything, human beings really started to understand what chemistry actually was. This started happening right around the end of the 18th century and the beginning of the 19th century. And of course, the chemists were looking at ways to use chemistry to push society forward. And they were looking at many, many different areas. And dye synthesis was, of course, one of them. Now, in 1856, a man by the name of William Perkins, he was a young English chemist and working for a German chemist by the name of Professor Hoffman. And at the time, they were attempting to synthesize quinine. And if you don't know what quinine is, it's an anti-malarial agent. At that time, it was the only known treatment for malaria. And of course, malaria was a real problem for many parts of the world at that time. And unfortunately, malaria is still a problem in some of the areas around the world, even to this day. But the idea that this group had was that if they can synthesize quinine, it would make it more readily available. Quinine comes from a natural tree in Central and South America, so you can imagine in the 1800s, it was difficult to isolate and then distribute around the world. So it was extremely expensive. And so they figured if they could synthesize it, then of course they would make lots of money. That was their one of their major driving forces, but it would also really, really help in terms of providing this extremely important drug to the rest of the world. And unfortunately, quinine was well beyond the methods and abilities of chemists at that time. This is the structure of quinine, and as you can see, it's a very complex molecule, and this just simply wasn't within the realm of the abilities of those particular chemists. And that didn't prevent them from trying. And of course, Perkins tried, but his method failed. Now, fortunately, Perkins stumbled across something during this process. The story goes is that he attempted this reaction in his apartment over the Easter break, and the reaction didn't work. He tried it multiple times and it just didn't simply work. And so at the end of the day, he started cleaning up all of his glassware, and he used alcohol to clean up his glassware. And when he added the alcohol to the reaction vessels, the story goes is that the solution turned a dark, dark purple. And Perkins noticed this and decided to try something, and so he took a piece of cloth, dipped it in the solution, and it dyed that particular cloth purple. Now, if you know anything about purple in terms of dyes, it's an extremely rare dye, and it was very, very expensive. In essence, the only people that could wear purple were the wealthy. And so Perkins knew immediately that he had stumbled on something um, potentially groundbreaking. And in fact, he had accidentally synthesized the very first synthetic dye. Today, it's called Perkins Mauve or Mauvine A. They're a class of them. And as you can see, here's the structure here. Um, and as I said, this is the very first synthetic dye. And with this accidental discovery, Perkins went on to become one of the pillars in the Industrial Revolution. And this started happening right around the mid 1800s. And one of the areas was, of course, the textile industry. And if you look at the big names in the Industrial Revolution, Perkins is right there because he was directly involved in the synthesis of dyes for the textile industry. So once the first synthetic dye was made, the chemists started trying to figure out what was going on. And eventually they really learned how color and structure are related. And so once the first one was made, it just kind of dominoed after that to the point of today where almost all um, dyes are synthetic. One of the interesting little twists of history, I'll circle back to quinine for just a little bit. Um, there was an eventual method made to synthesize quinine um, in the 1940s. However, it's now cheaper to isolate quinine from the natural source than it is to make it in the lab. It's kind of one of those funny little twists of history where it completely reverses. But anyways, now almost all dyes are synthetic, and one of the largest classes of dyes are known as the azo dyes. The basic structure of an azo dye is two aromatic rings stuck together between a nitrogen-nitrogen double bond. And what this double bond does is that it allows conjugation to exist between the two aromatic rings. And as you remember, as you get extended conjugation, the gap between the HOMO and the LUMO starts getting smaller and smaller and smaller. And so this extended conjugation is what leads to color. And the azo dyes is an extremely large family of dyes. And hopefully you can kind of understand why, because all you have to do is put different functional groups in the different positions on the aromatic ring, and in essence you get a whole new dye. The synthesis of azo dyes is a two-step process, and it starts with what's called diazotization. And that is where you take your aromatic amine. So for us, it is p-nitroaniline in the presence of hydrochloric acid and sodium nitrite to produce the azide salt. So this is the first step. So Then you do the second step of azodisynthesis, which is called diazonium coupling. And in essence, what this is an electrophilic aromatic substitution reaction. So we take our azide salt, and you add to it your second aromatic molecule, which for us is resorcinol. It's also known as 1,3-dihydroxybenzene, and it is also sometimes called 3-hydroxyphenol. So multiple names. We call it, its common name is resorcinol. And this is an electrophilic aromatic substitution reaction. Alcohols are ortho-para directors, and this is the carbon that attacks the nitrogen, giving us the final product. Azoviolet. And in fact, this is the only product from this reaction. Even though these are ortho-para directors, there is only one possible reaction product when you add these two molecules together. And the reason for that has to do with the orientation of the two alcohol groups on the aromatic ring. So if we take a quick look at that. And we draw it like this. So let's focus on this alcohol group first. So this particular hydrogen, or carbon, excuse me, is ortho, and this one is ortho to this alcohol, and this carbon is para to this alcohol. Now if we look at this alcohol, that carbon and that carbon are ortho, and that carbon is para. So because of the orientation of the two functional groups, they are directing the reaction to exactly the same three carbons. And these two carbons are identical to each other. And so because the reaction is not going to occur at this position because there's just too much steric hindrance, etc. there, the only reaction that's going to happen is at this position. And again, since these two carbons are identical to each other, you get the same product regardless. Okay, so again, azoviolet synthesis, very simple reaction, does not take much time. There is one minor hiccup to this, and that is product analysis. We can't do our standard product analysis of melting point because the product decomposes before it melts. So melting point is out, and the IR is beyond messe. So we're not going to take an IR. So we're going to analyze our product a little bit differently. The first thing that we're going to do is see, does our product behave like a dye? Azoviolet is a dye, and it should dye cotton. And so that's one of the things that we're going to see. And so we're going to take a piece of cotton and see if it dyes it orange. And the other thing we're going to do is take a look at the pH. Many azo dyes have different colors depending upon the pH. And azoviolet is no different here. So under acidic conditions, azoviolet is orange. And under basic conditions, azoviolet is purple. So we're simply going to see, does our product turn purple under basic conditions and remain orange under acidic conditions? And so that is the azoviolet synthesis. Again, like I said, very simple reaction. There are not a lot of difficulties associated with it, um, and very fast, etc. Product analysis is also, again, very, very simple. Okay, so that brings us the end to the synthesis of azoviolet. And again, our office hours for 128L are on Thursdays from 2 to 3. And if you're in 220C, the office hours are on Mondays and Thursdays from 5 to 6. And again, I also have the regular office hours that anybody can attend on Tuesdays and Wednesdays from 5 to 6. So if you have any questions, either send me an email or come to the office hours and ask them then. Until next time, we will see you later. Bye bye.